Welcome, everybody. We're excited today to have Vanessa Robins, who will tell us about correspondence of max flow to the absolute permeability of porous systems.
Yeah, thank you, Henry. It's always an honor to be able to give a talk to the AATRN series. And the material I'm going to present today is quite a physics applied talk, but maybe there'll be a bit of topology at the end. We'll see. Aside from the fact that we're looking at graphs. Yeah. So yeah, this project was kind of the final project under my future fellowship. And it was in collaboration primarily with Ryan Armstrong at the University of New South Wales. And he is an engineer, but has extremely strong mathematical knowledge and intuition. And it was through this project and his students who did all the hard work doing the simulations. Who else? And yeah, so I never met Zachar, Payman, or Alexander, but they obviously did all the simulation work that I'm going to show you. And my other colleague, Anna Herring, she's now faculty in the US. I think it might be Tennessee. She's also got an engineering background, and she and I did a lot of work on system homology of sandstones and correlating that to various properties of the way fluids flow through them. All right. Yeah, so, oh, hang on, cursor works. So basically in this talk today, I'm going to give you a brief background on the sorts of materials we've been looking at and the methods we've used to do that. I'm going to explain what permeability is at a very, first year engineering level, and then explain how we used this concept that hopefully is well known to you about when we're looking at flow through a graph, this theorem that tells us that the maximum flow you can put through a weighted graph from a source to a sink. So the maximum flow you can achieve is equal to the weight of the minimum cut on the edges. All right, hopefully this will get clear as I go. So this image here is an example of the small cylindrical core sample that my colleagues take out of a large rock, and they put it through an X-ray CT machine, and what they're rendering here is actually the pore space. So the stuff that looks a kind of gold color is actually the pores where the fluid would sit. Okay. So this micro CT facility has been running and developed since 2000. It was led by Mark Nackstead and Tim Senden, and Adrian Shepherd was, I think, leading a lot of the early numerical implementations for this stuff. So I guess this group's aim has always been to be able to get the same quality of data from a lab-based CT facilities as you would get from a synchrotron, right? So a synchrotron is, I don't know, has like a kilometer radius and is a huge facility using very high power, very coherent X-ray sources. So you can get images very quickly and very cleanly. This desktop machine, a lab-based machine, it's not quite desktop. It's like, this is about the height of a person and 2 meters wide, that machine down there. And so it takes a lot longer to get that type of image quality, and they use very, very fancy numerical implementations to reconstruct the internal data, but they really do get extremely good quality images out of this from a much smaller machine. Okay. And the sort of thing we want to be able to do when we look at these porous materials is to obtain geometric information such as the pore and grain size distribution, And obviously, the way they connect to each other is very important as well. So that's where the topology comes in. And they've also studied the structure of immiscible fluid distributions. So that could be oil and water, or it could be water and carbon dioxide. And then, yeah, so then the topological aspect that we obtain are things like the adjacencies between elements. So that would be grain adjacencies and also pore adjacencies in order to build network models. And then in terms of the physical applications, we want to correlate this geometric and topological structure with properties such as the way diffusion occurs through the pore space. I'm going to tell you about permeability today, but they've also been very interested in something called trapping capacity. So that's how, when you've got these immiscible fluids, how does one fluid get trapped by another fluid that gets kind of locked into the pore space purely by the physics and chemistry involved. And then in a whole other world of research, we also look at things like mechanical response to loads, so stresses and strains. Ooh. All right, so this slide is going to tell you about our basic image, like how we go from the CT data to something we can analyze the topology of. And we do this by, first of all, acquiring that 3D CT image. So each voxel in that image is proportional to the X-ray density of the material. Okay, so I'm not showing you that raw X-ray image here. I'm showing you what happens after my colleagues have run a segmentation algorithm, which labels each voxel as either grain. So in this picture here, we've got spherical grains, which are colored white, and then pore, which is the black pixels. So, excuse me. What do I need to say here? Yeah. So this was an extremely clean sample because we were just imaging silica beads. But when we're looking at real rocks, it can be a much more complicated issue to go about segmenting the samples into grain and pore. But I have, to the large part, left that to my colleagues to do that difficult part. The next step is that we compute a signed Euclidean distance function. So that means we have a function that is just each voxel is assigned the distance to the interface. So if I'm sitting on a black voxel, I'm going to give the negative of the distance to the interface. Yeah. And if I'm in a white voxel, I'm going to have the positive distance. So that's what these signed Euclidean distance functions are. And that gives a nice way of, it gives a really nice function that characterizes the geometry of the pore space in the negative parameter regime, and it characterizes the grain phase in the positive parameter regime. Okay, so here's a little example where I've taken a slightly noisier image than this one and done the lower level set filtration on that signed distance transform and computed the persistence diagrams. So you can see that for the pore space is characterized in the 0° 0 persistence diagram because the pore has the negative distances. You get a couple of points that have positive depth values here because of boundary effects, really. So there's a little bit of pore space that doesn't connect until we go into the positive level sets of the distance function. Yeah, and obviously these images are all 3-dimensional, and I'm just showing you 2D slices so that you can actually see what's going on. The degree 1 persistence diagram is then characterizing the number of redundant pathways through the pore space, basically. And we have some births and deaths within the pore space itself. So this means there's a kind of a very highly non-convex pore in the pore space where I generate a cycle in the within the pore space before that gets filled in. So I've got a degree index, I've got an index 2 saddle point in the distance function sitting in the pore space here. That's what that says. Most of our degree 1 persistent homology is in the negative birth, positive death. So that means these sorts of cycles are the ones that go around the grain contacts. Okay, you can't see these because I don't have the 3D picture, but you can think of these points here as representing cycles around the point where two beads are in contact. And then in the degree 2 persistence diagram, we are capturing information about the grains. So the births are some positive number here, and then the deaths are very distinctive because I have 3 different sizes of grain here. Okay, so these little clumps are, their death values are the radii of the 3 different sizes of grain. And then we get these streaky effects across different birth values, and they are all due to the boundary effects. So we've got these beads that get cut off along the edge of our square image domain. Okay, so that's what's causing this stuff here. Great, so hopefully that's giving you a bit of intuition to what these persistence diagrams tell you. And I'm going to do a little spruik for my Women in Computational Topology group, because we wrote a very nice little paper that talked about how when we change the resolution of our imaging, how does that impact the persistent homology of these sign distance transforms? Okay, so that I'm not talking about that today, but I just thought I'd throw it in because it's quite a nice little study. So the other sort of information, I guess for a long time, I was computing these persistence diagrams and we were hoping to find some signature of permeability out of them. And one promising step in that direction was that we could really see what's called the percolating radius, or the critical radius for the pore space. So this percolating radius is the radius of the largest sphere that can fit all the way through the pore space from top to bottom, okay? And so you could think of it as, when I'm doing that lower level set filtration, it's the threshold where the pore space spans from top to bottom of the sample. And that radius shows up very clearly in these persistence diagrams. And so that was a very interesting observation. And the reason it shows up in these diagrams is because you can think of our pore spaces as having some kind of continuous random distribution of pore sizes or grain sizes in the other phase. And because they're fairly homogeneously randomly distributed through the sample, what happens as we grow that lower level set is that they, first of all, connect to nearby pores will connect to each other. And then as we get to this critical radius, what happens is that we can suddenly connect the pore space across the full image domain. And that means we're now able to join the very largest pores from 2 previously disconnected components via what must have been a relatively very narrow throat. Okay, so that's why we're seeing this signature of percolation here. And so that's the grain phase percolation, and then this is the that's the pore phase percolation in PD0, and the grain phase percolation is showing up in PD2, so that we see a grain phase percolation, because if we're looking at a sandstone, they have made up of little sand grains that have undergone a lot of heat and pressure and fused together. Okay. So you can really think of this sandstone as being composed of two connected regions that are intricately threaded through each other. That's what we call bicontinuous. So they're bicontinuous structures because both phases are continuous throughout the sample. And so in PD1, these percolation thresholds show up as kind of bounding this very characteristic shape in the PD1 diagram. So yeah, so here we are. This is kind of as far as we got in terms of understanding permeability before we took a change in perspective to look at the max flow min cut type approach. All right, so I've been throwing this word around, permeability, and you'd probably like to know a bit more about what on earth that means. So the first thing I want to say is that permeability is not the same as porosity. So there's these two P words, porosity and permeability, that people talk about a lot when you're looking at a porous material. So porosity is just the raw volume fraction, yeah? So it's just the fraction of space that's occupied by one phase compared to the other phase, yeah? So it's the volume of the pore space divided by the volume of the entire cylinder. And then permeability is telling you something about how fluid can flow through that sample, yeah? And so obviously your volumes may be distributed throughout the cylinder in very different ways. And the way those volumes are distributed throughout the sample is going to dictate how well the fluid can flow through that pore, okay? And so this plot over here is really highlighting the fact that porosity is not directly correlated with permeability, yeah? So we're seeing if my porosity is here about 12%, if I draw a vertical line up from 12%, I'm seeing different materials with different permeabilities that are spanning 3 orders of magnitude, okay? So there's a huge difference in permeability even at a given porosity. Nevertheless, if we kind of categorize our materials into different classes, so that's what these different colored dots are doing. We've got a clay type material here, and then silty things. I'm not sure what the technical definition of silty is, but I guess you can kind of imagine. And then we have fine-grained sandstones with the green and coarse and very coarse versions thereof, okay? So when we restrict ourselves to a single type of material, we can get a vaguely functional relationship between porosity and permeability. And that's captured in something called the Cassini-Kármán equation. So here phi is the porosity, K is the permeability, and this constant of proportionality depends, it's just an empirical constant that comes from those different types of materials, okay? All right, so what exactly is permeability? It is capturing, it's a bit like resistivity maybe in an electronic material. It's really capturing some kind of constant of proportionality between the pressure difference and the length of the sample in order to tell us about this fluid, how fast the fluid is going to be coming out of the sample here. Sorry, that was totally garbled. So we're trying to understand if I maintain a particular pressure drop for the fluid across this sample, then that's going to make my fluid flow. And how fast is that fluid going to flow? That's going to depend on how far it's had to travel and this constant of proportionality, which is the permeability, okay? So the key things people measure are the flux, which is always represented by a Q. So flux is how much material is coming out per unit of time. The area is just the cross-sectional area of my sample, and the length is the distance through the sample. And then we're maintaining a pressure difference across that sample there. And we'll see that the fluid velocity then depends on permeability. And it also depends on this other parameter mu, which is the viscosity, right? So viscosity is measuring the thickness of the fluid. So water has a low viscosity, but honey has a very high viscosity. Yep. Okay, so this is how we empirically estimate permeability. We know something about the viscosity of our fluid. We can measure the flux. That's how much water is coming out the bottom of our sample. We know what the length and the area are, and we can also measure this pressure difference. Okay. And now our goal is to relate this value of K to the rock microstructure, right? So it's hopefully you can have some intuition that K is going to depend on the details of the way the pore space connects through this solid here. So the existing models are that Kozeny-Kármán equation, which depends on the class of material. And then there's another very popular and successful relationship called the Katz-Thompson cross-property relationship. So this is related permeability to electrical conductivity. So you can measure the electrical conductivity if you put a conducting fluid through your sample, like a salt brine. You can measure the relative conductivity through the sample versus the conductivity of the pure liquid. And then permeability is found to obey this cross-property relationship, where C prime is actually a predetermined constant and R crit is that percolating radius. Okay. All right, so here's how we're going to attack the problem today. We're going to use network models. So this is a very standard and popular method for simulating fluid flow through these very complex pore spaces. I think computers are probably powerful enough that you can now actually do image-based, what they call lattice-Boltzmann models. So you can actually simulate the fluid flow through the entire pore space on a much more fundamental level. But these network models are still popular because they allow you to simulate fluid flow through a much larger sample. And the basic idea here is that your pores are going to be modeled by spherical nodes, and the little constrictions between two of these larger openings are going to be modeled by a little cylinder. Hang on, I'm going to sneeze. Okay. So, yeah, so we can build there's many algorithms for taking a complex 3D geometry like this and turning it into a network model. And for this project, we used a package called PoreSpy. Okay. So this was the numerical simulations that were done by, oh, sorry, these are the people who've written the package, but the students on the first page were the people who did a lot of the simulating here. Okay, so what's this pore network model? It is a graph with weighted vertices and weighted edges. Yeah, so the vertex weight is going to be the volume of a pore body, and the edge weight is going to be a pair. It's going to contain both the radius and the length of one of these throats. So if you think back to the sine distance function that we calculated, the pores are basically at the local minima in that distance function, and the edges are going to be associated with the index 1 saddle points. Okay, so the radius is the the value of that index 1 saddle point, and the length is just going to be the distance. We're just going to take a straight edge distance between the two local minima that it joins. Okay, and then we model the fluid flow by replacing each edge with a cylindrical pipe. And then there's an analytical derivation for the conductivity through pipes, which gives us a parameter, which I call Cij here. So the Cij is the vertex pair for the edge, and it's going to be proportional to the 4th power of the radius. Okay, that's just for very smooth flow through a pipe, you can derive this expression analytically. And then the flux is calculated as the difference between the pressure at each end of the pipe times the conductivity of the pipe, blah, blah. Okay. Now, obviously, this is a really crude model of fluid flow through a complex geometric pore space, but my goal in this project was not to assess the validity of this network model. Okay, so other people have studied that in great depth, and there's all sorts of different ways to modify the model to get better agreement with the true physical complicated geometry. But my goal in this project is not to compare the network model with the true pore space. What I'm doing in this project is comparing results from the network model with this max flow min cut idea. Okay, just keep that in mind.
Vanessa, can I ask a question?
Yeah, go ahead.
So the vertex weights do matter in this model, is that right?
Not if, no, they don't, how do they don't model for the fluid flow, because we assume, well, actually we know that the vertex weight is always larger than the pore, the constriction through the pore, right? Because we're taking the most narrow radius for the pore throat. We know that the vertex weights aren't going to constrain the fluid flow at all.
Right. That makes sense.
Yeah, possibly they could if it was a very, very long and tortuous kind of throat. But I think because the geometric structure is so rough, it's always the case that the throats get broken up into small pieces. So all the volume is considered to lie in the pore body, and the edge weight is just telling us about the constriction, the narrowest point of that throat. And then the length is taken to be, yeah, like I said, the distance between the centers of the pores. So it's a really, really crude physical model. But yeah, basically in the rest of this study, we just kind of ignore the vertex weights. We're only worried about the edge weights.
Thanks.
So for physical consistency, we know that the flux at each vertex, the flux has to sum to 0. Okay, that's just conservation of mass. We can only have so much coming in and so much going out, and they have to balance. And then in actual experiments, and also in the numerics, we maintain the overall flux at a constant value of Q at the inlet and outlet. Yeah. So rather than setting the pressure at the top and the bottom, we're going to just set the flux. And people do that in experiments quite simply by attaching a pipe from the bottom of the sample to the top of the sample. And then conservation of mass immediately means that whatever's coming in has to be exactly equal to whatever was going out. Okay. All right, so we've got this graph, we've got weights on the edges, and we want to solve for the pressure at each vertex, given that we know the flux at the top and the bottom, And we know that at each vertex, the incoming balances the outgoing. Okay, so this expression here is just a big set of linear equations. So I can rewrite that as a matrix. And what I'm saying is that the things that multiply the pressure values at each vertex have to equal Q at the inlet, negative Q at the outlet, and 0 everywhere else, okay? So this matrix here that we get out of this physical equation is what we know as the weighted graph Laplacian. So that's kind of cool. And just to remind you, I've got a little note here. So the weighted graph Laplacian is found as follows. We set up a diagonal matrix of the edge weights, and then we take the edge vertex incidence matrix, which anyone who works in persistent homology will know as the boundary matrix that maps edges to vertices. So that's pretty cool. And the graph Laplacian is then just I transpose, okay? So it's not too hard to then solve for the pressures Pi. And also, so solving for the pressures means we're also solving for the pressure at the inlet and the pressure at the outlet. And so we use those two values. That's all we need out of this big equation is the inlet and the outlet difference in order to calculate the permeability for the whole sample. Okay. So this is our network model value for permeability. How am I going? Not too bad. So now we're going to talk about our max flow min cut setup. Okay. So the setup that's typical in these max flow min cut contexts is we have a weighted graph. Yeah. We have an inlet, a source, and we have an outlet or a sink. And these are the two distinguished vertices. And then a cut partitions all the vertices into two sets such that every vertex either belongs to the inlet set or the outlet set, right? So the two sets do not intersect and their union is everything. And the cut, the weight of the cut, or the cut itself is just the set of edges that join something in X with something in Y. Okay, so this could be X, and then that would be Y. And my cut is the edges that go between the two, and the weight is the sum of the edge weights in the cut. Yeah, so here I've got a 1, a 2, a 3, and a 3. So I can study all possible cuts for my graph and evaluate the weights, and then the minimum cut is a partition that achieves the minimum weight. So I can look here and I find a bunch of different weights. Oh, hang on. And it turns out that the minimum weight, I think, is 6. Okay. So this will be my minimum weight. So now we're going to look at what we mean by flow. So our flow is some function that assigns a value to each edge so that the function value is less than or equal to the weight, okay? So in this max flow min cut, the weights on the edges are absolute maximum values that we're not allowed to exceed. They're defining the true capacity of each carrying weight here. And then a flow is the total amount leaving the inlet, which has to equal the total amount coming into the outlet, right? Because we also impose this conservation of mass, that the sum of whatever's coming into the vertex has to equal whatever's going out, okay? All right, so on that particular example, we've assigned a function and we've calculated our total flow to be 4. But I can keep pushing through a little bit more flow, right? I hadn't reached the maximum capacity on my edges there. So I can increase the flow a little bit to now have a value of 5. And then I can increase through this pathway as well. And now I get a flow of 6. But now you'll see that I can't increase the flow at all because I've reached the maximum capacity of these edges through here, right? And if you remember, they were the edges in our cut. Okay, so a max flow is one that maximizes the total flow. And we know that for any cut, the sum of the flow values through the cut is constant, and we can obtain a minimum cut by setting the flow equal to the weights through that minimum cut, yeah? And then the max flow has to equal that minimum cut. Hopefully that's clear. All right, so now what we're going to do, oh, this is my, oh yes, okay. So now what we're going to do for our permeability study is we're going to set our weights equal to these conductivities. So remember, each edge was, we modeled by a little pipe, and we said the conductivity of an edge was the radius to the power of 4, and that is going to define our weights. And so we're going to now define our minimum cut version of permeability to be the sum of the capacities in a minimum cut, all right? And to get the dimensions correct, we have to divide by area, but that's also because we're really, the permeability is this kind of averaged property. It's something that we've averaged out over the cross-sectional area of the sample, okay? So I'd just like to point out that we're making a bit of a, I guess we're using this max flow min cut idea not in its strict sense, because we know that the flow in a pore network model is unbounded, yeah? So our flux through each edge, it does depend on the capacities, but it also depends on the pressure difference. So if I increase the pressure difference, I could increase the amount of flux going through, yeah? And so I don't have that absolute maximum in this permeability model of network flow, okay? So this is a bit of a kind of weird application of the idea, but we're going to test it and see what happens. So our hypothesis is that the minimum cut of these conductivities gives us an estimate of permeability, yeah? And what's interesting is that it's a purely geometric estimate, okay? We're not using anything other than the radii of the throats and the area of the sample, cross-sectional area of the sample. Okay. So my colleagues did all these wonderful experiments where they simulated some porous materials. And again, that porous material simulation comes out of that PoreSpy package. So they simulate the material, they build the network model, and then they run the standard network flow calculation of permeability. And then they also calculate the min cut version of the network, okay? So in addition to all these simulated porous materials, we had 4 real porous materials, and they are a very, very different characteristic, geometric characteristics. And this is the result we get. So the 4 real materials had a very big span in terms of their permeabilities. Oh yeah, so what I'm plotting here is the network permeability calculation versus our min cut approximation, yeah? And you can see it scales reasonably well over many orders of magnitude. So that's a pretty nice result, I think. And it also captures the scaling of the 4 very different materials. Okay, so it's a relationship that is not really dependent on material type. Remember, we saw other relationships dependent on whether it was a clay or a sandstone, and whether it was a coarse sandstone or a fine sandstone, etc. Okay. So this is a really pretty nice result, I think, and surprising for my engineering colleagues because they didn't think it would do so well. All right, so let's try and explain what we're seeing, okay? What we're seeing is that typically, but not always, the network value is larger than the min cut estimate, yeah? So most of these points are falling below the diagonal, so that's saying the network model value is larger, but there are definitely a few points here which are above the diagonal, okay? So why would that happen? What's going on? And I guess the reason it's giving us, so when the network model and the min cut model will agree, they'll be identical if we assume that the length divided by the pressure drop is constant across the sample. So that's saying, right, so remember I had the pressure at the inlet, the pressure at the outlet, and I had to divide by the distance traveled, the whole length of the sample. So if it's the case that all the pressure drops across each little edge are basically, if those pressure drops are proportional to the length of each edge, then we will see that Kn equals Kc, okay? And obviously this is a pretty major approximation to make, but it's not so bad. So let's try and understand a few more details here. So this was where I got to put on my theoretical physics hat and start with the most simple toy model possible and do a little analytic scaling analysis. So now we're going to imagine our network model consists of just 3 pores and 2 pipes, yeah? And if I set that up, I've just got a very simple, I've got like a 3x3 linear system, and I can calculate exactly what that solution has to be. And we see that the pressure difference is equal to length on capacity for the first pipe plus the length on capacity of the second one, yeah? And if we just go through a bit more algebraic manipulation, we'll see that the network model of permeability is equal to the min cut permeability times this factor, right? Length over this. So so now I can look at some limiting cases. So the first one is if the lengths are the same and the capacities are the same, then I've got a single pipe, and so network is the same as min cut permeability. If my pipes are the same length and very straight, right? So the fact that the 2 edge lengths are equal to L on 2 means my network is just going straight through the sample here. But if the capacities are very different, then I can see the network permeability approaching 2 times the min cut permeability. Okay, so that's why we see network permeability larger than the min cut one. And then if the capacities are equal, yeah, so the pipes have the same radius, but the path is quite tortuous, right? So here I'm saying the individual pipes are maybe taking a very much longer distance than the distance through the core sample. When that happens, I see that the network permeability is equal to the min cut capacity divided by this ratio tau, okay? So tau is always going to be bigger than 1, and it's when it is significantly larger than 1 that we see the network permeability being smaller than the min cut permeability, okay? And so that was, I think, quite a nice way to explain that graph here. Okay. So I'm only going to see points above this diagonal when there are very tortuous paths through the network and with maybe quite similar capacities. Oh yeah, so I did repeat the picture here. So here's the general picture. If the network permeability bigger than min cut means I've got highly variable conductivities, whereas network permeability less than the min cut means I have very tortuous flow paths. Okay. So I think this is a really nice little story, and it basically boils down, as I say here, to this bundle of pipes model, which is basically that you've got some number of, the min cut is representing some number of independent flow paths through the pore space, and the weight of the min cut is kind of they're the critical restrictions on those independent flow paths. And the approximation will be worse when you have a greater breadth in your distribution of geometric parameters. Okay. And so I don't know how earth-shatteringly original this conclusion is. It's because engineers have always understood flow through a porous material via this bundle of pipes model. But I feel like I've finally made a derivation that makes sense to me, because I never understood how they arrived at this picture before. But now it is clear in my head, at least. Cool. Yeah, so again, thanks to all my co-authors who did the hard work on this one. And I'm happy to answer any questions you might have.
Before we get to questions, let's briefly unmute ourselves and thank the speaker. All right. Questions? Atish.
I have only one question, which intrigues me. Towards the beginning, when you shows the persistence diagrams, you said that the critical percolating radii are significant features there.
Yeah.
So could you explain this a little more? I didn't quite get it.
Yeah. So I think what's the easiest one to understand, I think, is thinking about this pore space and a minimal spanning tree type model. So okay, so if you think a bit more in terms of that network model, yeah, we've got the nodes are being given by the local minima of the distance transform. So they're actually the centers of the pores. Yeah. And then when so the births of the connector components are local minima of my signed distance function, yeah? So where's my, okay, so the local minima are at these centers of these pores.
Yeah.
And then and they correspond to the births in PD0. So now when I connect two local minima together via the connections between two local minima occur when my distance function raises up through that index 1 saddle point. Yep. And that index 1 saddle point is associated with a throat, a constriction in the pore space. Okay. So what we think about now is that, so you could think maybe you've got some network through your three-dimensional space, and the weights on the vertices are the local minima in the pore space, and the weights on the edges are the index 1 saddles. Yep. And now I'm just going to connect my graph. So now I've got kind of something like a random graph structure, and I'm adding vertices and edges according to their weights in order from smallest to largest. And when I'm working with a sandstone here, I've got the weights are coming, the pore sizes are coming from some continuous random distribution, and the throats are also coming from a fairly continuous random distribution. Yeah. And so initially when I join two pores together to get the index 1 pores that connect two pores, or the index 1 critical points, so the edge weights that are associated with joining two pores, they typically are going to join pores that are next to each other, yeah? And so they give me births and deaths that are fairly close to the diagonal.
Yes.
But it's only when I get to the point, and in persistent homology, I always pair with the local minimum that's closest to me in value. So when I add an edge in this graph model, I'm going to pair that edge, which represents a death, with the local minimum, and each of my two components, I'm going to pair with the one that's closest to me in value. Yep. And so typically those values are fairly close to each other until I'm nearing the percolation threshold. So when I hit the percolation threshold, suddenly I'm joining very large components to each other, and so each component is always saving its deepest minimum, right? And so when I'm joining two large components together at this critical percolating length scale, I'm finally able to pair a very deep local minimum with a narrow throat. Yeah.
Thank you.
Yeah. Cool.
I wanted to ask, what came first, the experiments where you found this nice new diagonal line, or their derivation, or was it sort of a back and forth?
Yeah, it was a bit of back and forth because because we were definitely testing this min cut idea, yeah. So here we were just testing the min cut idea to see how valid is that, yeah. And so we did the numerical experiments first, and it showed up this quite nice result. And then, so then it was afterwards that I was sat down to try and explain why are we seeing such a nice result. Yeah. Yeah.
Very nice. Haruhisa, please go ahead.
Oh, thank you for your talk, Vanessa.
Lisa.
Yeah.
Yeah.
My question is that you're using two different models of the graphs, and I was wondering why you use different weights in those graphs. So the edge weights are different. In network models, you use the C over mu L, and the min cut model, you're going to use the C. So what is some kind of physical intuition?
Yeah, so let's where do I spell that out? Is that here? Is that kind of this should have it all. So why do we use those as the weights? I think it just made sense from the physical perspective. So in the network model, we definitely, this is modeling the physics of the flow through the network. Yeah, the fact that the flux is proportional to the difference in pressure divided by the length. So it's the difference in pressure and that's allowed to vary with the flux. Yeah, whereas this weight Cij and the length are geometric parameters that are kind of set by the geometry. Yeah,
Mhm.
but the flux and the pressure are the things that are allowed to vary. So then the question is, why do we just look at these weights, the radii, and not the length as well? And I think the reason for that is because we expect the pressure difference to be proportional to this length. Yeah. So that's a kind of physics model here, that we always expect the pressure difference to be proportional to the length.
Oh.
Yeah.
Mm-hmm.
Yeah.
Yeah.
And so it made sense to take the min cut as being proportional to these capacities, the radii of the capacities.
Mm. Oh, right. Thanks.
Yeah. I hope
Yeah.
that explains. Yeah.
Yeah. Thank you.
You're welcome.
Any final questions? Well, if not, thanks so much, Vanessa, and we'll end the recording here.
Yeah, thank you very much. Yeah, and thanks for attending.